Uranus, from the Latin name Uranus for the Greek god Omicron Rho Alpha Nu Sigma, is the seventh planet from the Sun. It has the third largest planetary radius and fourth largest planetary mass in the solar system. Uranus is similar in composition to Neptune, and both have bulk chemical compositions which differ from that of the larger gas giants Jupiter and Saturn. For this reason, scientists often classify Uranus and Neptune as ice giants to distinguish them from the gas giants. Uranus' atmosphere is similar to Jupiter's and Saturn's in its primary composition of hydrogen and helium, but it contains more ices such as water, ammonia, and methane, along with traces of other hydrocarbons. It has the coldest planetary atmosphere in the solar system, with a minimum temperature of 49 K, minus 224 degrees Celsius, minus 371 degrees Fahrenheit, and has a complex, layered cloud structure with water thought to make up the lowest clouds and methane the uppermost layer of clouds. The interior of Uranus is mainly composed of ices and rock. Like the other giant planets, Uranus has a ring system, a magnetosphere, and numerous moons. The Uranian system has a unique configuration because its axis of rotation is tilted sideways, nearly into the plane of its solar orbit. Its north and south poles, therefore, lie where most other planets have their equators. In 1986, images from Voyager 2 showed Uranus as an almost featureless planet in visible light, without the cloud bands or storms associated with the other giant planets. Observations from Earth have shown seasonal change and increased weather activity as Uranus approached its equinox in 2007. Wind speeds can reach 250 meters per second, 900 kilometers per hour, 560 miles per hour. Uranus is the only planet whose name is derived directly from a figure from Greek mythology, from the Latinized version of the Greek god of the sky Uranus. History. Like the classical planets, Uranus is visible to the naked eye, but it was never recognized as a planet by ancient observers because of its dimness and slow orbit. Sir William Herschel announced its discovery on March 13, 1781, expanding the known boundaries of the solar system for the first time in history and making Uranus the first planet discovered with a telescope. Discovery. Uranus had been observed on many occasions before its recognition as a planet, but it was generally mistaken for a star. Possibly the earliest known observation was by Hipparchus, who in 128 BC might have recorded it as a star for his star catalogue that was later incorporated into Ptolemy's Almagest. The earliest definite sighting was in 1690, when John Flamsteed observed it at least 6 times, cataloguing it as 34 Tauri. The French astronomer Pierre-Charles Lemonnier observed Uranus at least 12 times between 1750 and 1769, including on 4 consecutive nights. Sir William Herschel observed Uranus on March 13, 1781 from the garden of his house at 19 New King Street in Bath, Somerset, England, now the Herschel Museum of Astronomy, and initially reported it, on April 26, 1781, as a comet. With a telescope, Herschel engaged in a series of observations on the parallax of the fixed stars. Herschel recorded in his journal, in the quartile near Zeta Tauri, either a nebulous star or perhaps a comet. On 17th of March he noted, "I looked for the comet or nebulous star and found that it is a comet, for it has changed its place." When he presented his discovery to the Royal Society, he continued to assert that he had found a comet, but also implicitly compared it to a planet. "The power I had on when I first saw the comet was 227. From experience I know that the diameters of the fixed stars are not proportionally magnified with higher powers, as planets are, therefore I now put the powers at 460 and 932, and found that the diameter of the comet increased in proportion to the power, as it ought to be, on the supposition of its not being a fixed star, while the diameters of the stars to which I compared it were not increased in the same ratio. Moreover, the comet being magnified much beyond what its light would admit of, appeared hazy and ill-defined with these great powers, while the stars preserved that luster and distinctness which from many thousand observations I knew they would retain. The sequel has shown that my surmises were well founded, this proving to be the comet we have lately observed." Herschel notified the Astronomer Royal Neville Maskelyne of his discovery and received this flummoxed reply from him on April 23, 1781, "I don't know what to call it. It is as likely to be a regular planet moving in an orbit nearly circular to the Sun as a comet moving in a very eccentric ellipsis. I have not yet seen any coma or tail to it." Although Herschel continued to describe his new object as a comet, other astronomers had already begun to suspect otherwise. Finnish-Swedish astronomer Anders Johan Lexell, working in Russia, was the first to compute the orbit of the new object. Its nearly circular orbit led him to a conclusion that it was a planet rather than a comet. Berlin astronomer Johann Elort described Herschel's discovery as a moving star that can be deemed a hitherto unknown planet-like object circulating beyond the orbit of Saturn. Bode concluded that its near-circular orbit was more like a planet's than a comet's. The object was soon universally accepted as a new planet. By 1783, Herschel acknowledged this to Royal Society President Joseph Banks. "By the observation of the most eminent astronomers in Europe, it appears that the new star, which I had the honor of pointing out to them in March 1781, is a primary planet of our solar system." In recognition of his achievement, King George III gave Herschel an annual stipend of £200 on condition that he moved to Windsor so that the royal family could look through his telescopes, equivalent to £24,000 in 2018. Name. The name of Uranus references the ancient Greek deity of the sky Uranus, ancient Greek, Omicron Rho Alpha Nu Sigma, the father of Cronus, Saturn, and grandfather of Zeus, Jupiter, which in Latin became Uranus, Latin pronunciation, Urans. It is the only planet whose name is derived directly from a figure of Greek mythology. The adjectival form of Uranus is Uranian. The pronunciation of the name Uranus preferred among astronomers is, with stress on the first syllable as in Latin Uranus, in contrast to, with stress on the second syllable and a long A, though both are considered acceptable. Consensus on the name was not reached until almost 70 years after the planet's discovery. During the original discussions following discovery, Maskelyne asked Herschel to do the astronomical world the favor, to give a name to your planet, which is entirely your own, and, which we are so much obliged to you for the discovery of. In response to Maskelyne's request, Herschel decided to name the object Georgium Sidus, George's star, or the Georgian planet in honor of his new patron, King George III. He explained this decision in a letter to Joseph Banks. In the fabulous ages of ancient times, the appellations of Mercury, Venus, Mars, Jupiter and Saturn were given to the planets, as being the names of their principal heroes and divinities. In the present more philosophical era, it would hardly be allowable to have recourse to the same method and call it Juno, Pallas, Apollo or Minerva, for a name to our new heavenly body. The first consideration of any particular event, or remarkable incident, seems to be its chronology, if in any future age it should be asked, when this last found planet was discovered. It would be a very satisfactory answer to say, in the reign of King George III. Herschel's proposed name was not popular outside Britain, and alternatives were soon proposed. Astronomer Jerome Lalande proposed that it be named Herschel in honor of its discoverer. Swedish astronomer Erik Prosperin proposed the name Neptune, which was supported by other astronomers who liked the idea to commemorate the victories of the British Royal Naval Fleet in the course of the American Revolutionary War by calling the new planet even Neptune George III or Neptune Great Britain. In a March 1782 treatise, Bode proposed Uranus, the Latinized version of the Greek god of the sky, Uranus. Bode argued that the name should follow the mythology so as not to stand out as different from the other planets, and that Uranus was an appropriate name as the father of the first generation of the Titans. He also noted that elegance of the name in that just as Saturn was the father of Jupiter, the new planet should be named after the father of Saturn. In 1789, Bode's Royal Academy colleague Martin Klaproth named his newly discovered element uranium in support of Bode's choice. Ultimately, Bode's suggestion became the most widely used, and became universal in 1850 when the Nautical Almanac Office, the final holdout, switched from using Georgium Sidus to Uranus. Uranus has two astronomical symbols. The first to be proposed, was suggested by Lalande in 1784. In a letter to Herschel, Lalande described it as un globe surmonté par la première lettre de votre nom, a globe surmounted by the first letter of your surname. A later proposal, is a hybrid of the symbols for Mars and the Sun because Uranus was the sky in Greek mythology, which was thought to be dominated by the combined powers of the Sun and Mars. Uranus is called by a variety of translations in other languages. In Chinese, Japanese, Korean, and Vietnamese, its name is literally translated as the Sky King Star. In Thai, its official name is Dao Uranat, as in English. Its other name in Thai is Dao Maratayu, Star of Mritu, after the Sanskrit word for death, Mritu. In Mongolian, its name is Tinjurim Van, translated as King of the Sky, reflecting its namesake God's role as the ruler of the heavens. In Hawaiian, its name is Helakala, a loan word for the discoverer Herschel. In Maori, its name is Ringi. Orbit and rotation. Uranus orbits the Sun once every 84 years, taking an average of 7 years to pass through each constellation of the zodiac. In 2033, the planet will have made its third complete orbit around the Sun since being discovered in 1781. The planet has returned to the point of its discovery northeast of Zeta Tauri twice since then, in 1862 and 1943, one day later each time as the precession of the equinoxes has shifted it 1 degree west every 72 years. Uranus will return to this location again in 2030-31. Its average distance from the Sun is roughly 20 astronomical units, 3 billion km, 2 billion mile. The difference between its minimum and maximum distance from the Sun is 1.8 astronomical units, larger than that of any other planet, though not as large as that of dwarf planet Pluto. The intensity of sunlight varies inversely with the square of distance, and so on Uranus, at about 20 times the distance from the Sun compared to Earth, it is about 1/400 the intensity of light on Earth. Its orbital elements were first calculated in 1783 by Pierre-Simon Laplace. With time, discrepancies began to appear between the predicted and observed orbits, and in 1841, John Couch Adams first proposed that the differences might be due to the gravitational tug of an unseen planet. In 1845, Urbain Le Verrier began his own independent research into Uranus' orbit. On September 23, 1846, Johann Gottfried Galle located a new planet, later named Neptune, at nearly the position predicted by Le Verrier. The rotational period of the interior of Uranus is 17 hours, 14 minutes. As on all the giant planets, its upper atmosphere experiences strong winds in the direction of rotation. At some latitudes, such as about 60 degrees south, visible features of the atmosphere move much faster, making a full rotation in as little as 14 hours. Axial tilt. The Uranian axis of rotation is approximately parallel with the plane of the Solar System, with an axial tilt of 97.77 degrees as defined by prograde rotation. This gives it seasonal changes completely unlike those of the other planets. Near the solstice, one pole faces the Sun continuously and the other faces away. Only a narrow strip around the equator experiences a rapid day-night cycle, but with the Sun low over the horizon. At the other side of Uranus' orbit, the orientation of the poles towards the Sun is reversed. Each pole gets around 42 years of continuous sunlight, followed by 42 years of darkness. Near the time of the equinoxes, the Sun faces the equator of Uranus, giving a period of day-night cycles similar to those seen on most of the other planets. Uranus reached its most recent equinox on December 7, 2007. One result of this axis orientation is that, averaged over the Uranian year, the polar regions of Uranus receive a greater energy input from the Sun than its equatorial regions. Nevertheless, Uranus is hotter at its equator than at its poles. The underlying mechanism that causes this is unknown. The reason for Uranus' unusual axial tilt is also not known with certainty, but the usual speculation is that during the formation of the Solar System, an Earth-sized protoplanet collided with Uranus, causing the skewed orientation. Research by Jacob Kedgeris of Durham University suggests that the tilt resulted from a rock larger than the Earth crashing into the planet 3 to 4 billion years ago. Uranus' south pole was pointed almost directly at the Sun at the time of Voyager 2's flyby in 1986. The labeling of this pole as south uses the definition currently endorsed by the International Astronomical Union, namely that the north pole of a planet or satellite is the pole that points above the invariable plane of the solar system, regardless of the direction the planet is spinning. A different convention is sometimes used, in which a body's north and south poles are defined according to the right-hand rule in relation to the direction of rotation. Visibility. The mean apparent magnitude of Uranus is 5.68 with a standard deviation of 0.17, while the extremes are 5.38 and plus 6.03. This range of brightness is near the limit of naked eye visibility. Much of the variability is dependent upon the planetary latitudes being illuminated from the Sun and viewed from the Earth. Its angular diameter is between 3.4 and 3.7 arcseconds, compared with 16 to 20 arcseconds for Saturn and 32 to 45 arcseconds for Jupiter. At opposition, Uranus is visible to the naked eye in dark skies, and becomes an easy target even in urban conditions with binoculars. In large diameter telescopes with an objective diameter of between 15 and 23 centimeters, Uranus appears as a pale cyan disk with distinct limb darkening. With a large telescope of 25 centimeters or wider, cloud patterns, as well as some of the larger satellites, such as Titania and Oberon, may be visible. Physical characteristics. Internal structure. Uranus' mass is roughly 14.5 times that of Earth, making it the least massive of the giant planets. Its diameter is slightly larger than Neptune's at roughly 4 times that of Earth. A resulting density of 1.27 grams/cm3 makes Uranus the second least dense planet, after Saturn. This value indicates that it is made primarily of various ices, such as water, ammonia, and methane. The total mass of ice in Uranus' interior is not precisely known, because different figures emerge depending on the model chosen. It must be between 9.3 and 13.5 Earth masses. Hydrogen and helium constitute only a small part of the total, with between 0.5 and 1.5 Earth masses. The remainder of the non-ice mass, 0.5 to 3.7 Earth masses, is accounted for by rocky material. The standard model of Uranus' structure is that it consists of 3 layers, a rocky, silicate/iron nickel, core in the center, an icy mantle in the middle and an outer gaseous hydrogen, helium envelope. The core is relatively small, with a mass of only 0.55 Earth masses and a radius less than 20% of Uranus. The mantle comprises its bulk, with around 13.4 Earth masses, and the upper atmosphere is relatively insubstantial, weighing about 0.5 Earth masses and extending for the last 20% of Uranus' radius. Uranus' core density is around 9 grams/cm3, with a pressure in the center of 8 million bars, 800 gigapascals, and a temperature of about 5000 K. The ice mantle is not in fact composed of ice in the conventional sense, but of a hot and dense fluid consisting of water, ammonia and other volatiles. This fluid, which has a high electrical conductivity, is sometimes called a water-ammonia ocean. The extreme pressure and temperature deep within Uranus may break up the methane molecules, with the carbon atoms condensing into crystals of diamond that rain down through the mantle like hailstones. Very high pressure experiments at the Lawrence Livermore National Laboratory suggest that the base of the mantle may comprise an ocean of liquid diamond, with floating solid diamond bergs. Scientists also believe that rainfalls of solid diamonds occur on Uranus, as well as on Jupiter, Saturn, and Neptune. The bulk compositions of Uranus and Neptune are different from those of Jupiter and Saturn, with ice dominating over gases, hence justifying their separate classification as ice giants. There may be a layer of ionic water where the water molecules break down into a soup of hydrogen and oxygen ions, and deeper down superionic water in which the oxygen crystallizes but the hydrogen ions move freely within the oxygen lattice. Although the model considered above is reasonably standard, it is not unique. Other models also satisfy observations. For instance, if substantial amounts of hydrogen and rocky material are mixed in the ice mantle, the total mass of ices in the interior will be lower, and, correspondingly, the total mass of rocks and hydrogen will be higher. Presently available data does not allow a scientific determination which model is correct. The fluid interior structure of Uranus means that it has no solid surface. The gaseous atmosphere gradually transitions into the internal liquid layers. For the sake of convenience, a revolving oblate spheroid set at the point at which atmospheric pressure equals 1 bar, 100 kilopascals, is conditionally designated as a surface. It has equatorial and polar radii of 25,559 plus minus 4 kilometers, 15,881.6 plus minus 2.5 miles, and 24,973 plus minus 20 kilometers, 15,518 plus minus 12 miles, respectively. This surface is used throughout this article as a 0 point for altitudes. Internal heat. Uranus' internal heat appears markedly lower than that of the other giant planets. In astronomical terms, it has a low thermal flux. Why Uranus' internal temperature is so low is still not understood. Neptune, which is Uranus' near twin in size and composition, radiates 2.61 times as much energy into space as it receives from the Sun, but Uranus radiates hardly any excess heat at all. The total power radiated by Uranus in the far infrared, that is heat, part of the spectrum is 1.06 plus minus 0.08 times the solar energy absorbed in its atmosphere. Uranus heat flux is only 0.042 plus minus 0.047 W/m2, which is lower than the internal heat flux of Earth of about 0.075 W/m2. The lowest temperature recorded in Uranus' tropopause is 49 K, minus 224.2 degrees Celsius, minus 371.5 degrees Fahrenheit, making Uranus the coldest planet in the solar system. One of the hypotheses for this discrepancy suggests that when Uranus was hit by a supermassive impactor, which caused it to expel most of its primordial heat, it was left with a depleted core temperature. This impact hypothesis is also used in some attempts to explain the planet's axial tilt. Another hypothesis is that some form of barrier exists in Uranus' upper layers that prevents the core's heat from reaching the surface. For example, convection may take place in a set of compositionally different layers, which may inhibit the upward heat transport. Perhaps double diffusive convection is a limiting factor. Atmosphere. Although there is no well-defined solid surface within Uranus' interior, the outermost part of Uranus' gaseous envelope that is accessible to remote sensing is called its atmosphere. Remote sensing capability extends down to roughly 300 kilometers below the 1 bar, 100 kilopascals, level, with a corresponding pressure around 100 bar, 10 megapascals, and temperature of 320 K, 47 degrees Celsius, 116 degrees Fahrenheit. The tenuous thermosphere extends over 2 planetary radii from the nominal surface, which is defined to lie at a pressure of 1 bar. The Uranian atmosphere can be divided into 3 layers: the troposphere, between altitudes of minus 350 kilometers, minus 186 and 31 miles, and pressures from 100 to 0.1 bar, 10 megapascals to 10 kilopascals, the stratosphere, spanning altitudes between 50 and 4,000 kilometers, 31 and 2,485 miles, and pressures of between 0.1 and 10-10 bar, 10 kilopascals to 10 micropascals, and the thermosphere extending from 4,000 kilometers to as high as 50,000 kilometers from the surface. There is no mesosphere. Composition. The composition of Uranus' atmosphere is different from its bulk, consisting mainly of molecular hydrogen and helium. The helium molar fraction, that is the number of helium atoms per molecule of gas, is 0.15 plus minus 0.03 in the upper troposphere, which corresponds to a mass fraction 0.26 plus minus 0.05. This value is close to the protosolar helium mass fraction of 0.275 plus minus 0.01, indicating that helium has not settled in its center as it has in the gas giants. The third most abundant component of Uranus' atmosphere is methane, CH. 4. Methane has prominent absorption bands in the visible and near-infrared, IR, making Uranus aquamarine or cyan in color. Methane molecules account for 2.3% of the atmosphere by molar fraction below the methane cloud deck at the pressure level of 1.3 bar, 130 kilopascals. This represents about 20 to 30 times the carbon abundance found in the Sun. The mixing ratio is much lower in the upper atmosphere due to its extremely low temperature, which lowers the saturation level and causes excess methane to freeze out. The abundances of less volatile compounds such as ammonia, water, and hydrogen sulfide in the deep atmosphere are poorly known. They are probably also higher than solar values. Along with methane, trace amounts of various hydrocarbons are found in the stratosphere of Uranus, which are thought to be produced from methane by photolysis induced by the solar ultraviolet, UV, radiation. They include ethane, C. 2H. 6. Acetylene, C. 2H. 2. Methylacetylene, CH. 3C. 2H, and diacetylene, C. 2HC. 2H. Spectroscopy has also uncovered traces of water vapor, carbon monoxide and carbon dioxide in the upper atmosphere, which can only originate from an external source such as infalling dust and comets. Troposphere. The troposphere is the lowest and densest part of the atmosphere and is characterized by a decrease in temperature with altitude. The temperature falls from about 320 K, 47 degrees Celsius, 116 degrees Fahrenheit, at the base of the nominal troposphere at -300 km to 53 K, -220 degrees Celsius, -364 degrees Fahrenheit, at 50 km. The temperatures in the coldest upper region of the troposphere, the tropopause, actually vary in the range between 49 and 57 K, -224 and -216 degrees Celsius, -371 and -357 degrees Fahrenheit, depending on planetary latitude. The tropopause region is responsible for the vast majority of Uranus' thermal far-infrared emissions, thus determining its effective temperature of 59.1 ±0.3 K, -214.1 ±0.3 degrees Celsius, -353.3 ± half a degree Fahrenheit. The troposphere is thought to have a highly complex cloud structure. Water clouds are hypothesized to lie in the pressure range of 50 to 100 bar, 5 to 10 megapascals, ammonium hydrosulfide clouds in the range of 20 to 40 bar, 2 to 4 megapascals, ammonia or hydrogen sulfide clouds at between 3 and 10 bar, 0.3 and 1 megapascal, and finally directly detected thin methane clouds at 1 to 2 bar, 0.1 to 0.2 megapascals. The troposphere is a dynamic part of the atmosphere, exhibiting strong winds, bright clouds and seasonal changes. Upper atmosphere. The middle layer of the Uranian atmosphere is the stratosphere, where temperature generally increases with altitude from 53 K, -220 degrees Celsius, -364 degrees Fahrenheit, in the tropopause to between 800 and 850 K, 527 and 577 degrees Celsius, 980 and 1070 degrees Fahrenheit, at the base of the thermosphere. The heating of the stratosphere is caused by absorption of solar UV and IR radiation by methane and other hydrocarbons, which form in this part of the atmosphere as a result of methane photolysis. Heat is also conducted from the hot thermosphere. The hydrocarbons occupy a relatively narrow layer at altitudes of between 100 and 300 km, corresponding to a pressure range of 1000 to 10 pascals and temperatures of between 75 and 170 K, -198 and -103 degrees Celsius, -325 and -154 degrees Fahrenheit. The most abundant hydrocarbons are methane, acetylene and ethane with mixing ratios of around 10-7 relative to hydrogen. The mixing ratio of carbon monoxide is similar at these altitudes. Heavier hydrocarbons and carbon dioxide have mixing ratios 3 orders of magnitude lower. The abundance ratio of water is around 7 times 10⁻⁹. Ethane and acetylene tend to condense in the colder lower part of stratosphere and tropopause, below 10 mbar level, forming haze layers, which may be partly responsible for the bland appearance of Uranus. The concentration of hydrocarbons in the Uranian stratosphere above the haze is significantly lower than in the stratospheres of the other giant planets. The outermost layer of the Uranian atmosphere is the thermosphere and corona, which has a uniform temperature around 800 to 850 K. The heat sources necessary to sustain such a high level are not understood, as neither the solar UV nor the auroral activity can provide the necessary energy to maintain these temperatures. The weak cooling efficiency due to the lack of hydrocarbons in the stratosphere above 0.1 mbar pressure level may contribute too. In addition to molecular hydrogen, the thermosphere corona contains many free hydrogen atoms. Their small mass and high temperatures explain why the corona extends as far as 50,000 kilometers, 31,000 miles, or 2 Uranian radii, from its surface. This extended corona is a unique feature of Uranus. Its effects include a drag on small particles orbiting Uranus, causing a general depletion of dust in the Uranian rings. The Uranian thermosphere, together with the upper part of the stratosphere, corresponds to the ionosphere of Uranus. Observations show that the ionosphere occupies altitudes from 2,000 to 10,000 kilometers, 1,200 to 6,200 miles. The Uranian ionosphere is denser than that of either Saturn or Neptune, which may arise from the low concentration of hydrocarbons in the stratosphere. The ionosphere is mainly sustained by solar UV radiation and its density depends on the solar activity. Auroral activity is insignificant as compared to Jupiter and Saturn. Uranus atmosphere. 2011 QF99 and 2014 YX49, the only two known Uranus trojans. Colonization of Uranus. Extraterrestrial diamonds, thought to be abundant in Uranus. Uranus in astrology. Uranus in fiction. Notes. References. Further reading. Alexander, author of Francis O'Donnell, 1965. The Planet Uranus, A History of Observation, Theory, and Discovery. Minor, LSD. 1998. Uranus, the Planet, Rings, and Satellites. New York, John Wiley & Sons. ISBN 978-0471-97398-0. Bode, Johann Alert, 1784. Von dem Neuen Planeten. Von dem Neuen Planeten. Bei dem Professor, etc., Bibcode :1784 DOI 10.3931/ERARA1454. Gore, Rick, August 1986. Uranus, Voyager visits a dark planet. National Geographic. Volume 170 No. 2. Pages 178 to 194. ISSN 00279358. OCLC 643483454. External links.